Hi, my name is Gabriela and I'm a PhD student at Johannes Kepler University Linz. I will present Locating Feature Revisions in Software Systems Evolving in Space and Time. This is a joint work with David, Lucas, Wesley, Paul, and Alexander. Software companies have to face evolution in space due to different customers with different requirements, scenarios, platforms, and operational systems, resulting in many products of a system. The software product line is an approach which consists of a common core and a set of features that can be used to compose many variants of a system. Still, software companies have to face evolution in time and keep variants updated with the maintenance tasks, as for example, bug fixing features. The version control systems are sophisticated to support to implement and track changes over time. However, they do not provide a support for tackle evolution in space. Despite version control systems can be used as a clonal mechanism, they are difficult to maintain the system variability with the evolution over time. As for example, if we have a bug in a product that was used for cloning many other products of a system. Even we have variability mechanisms as preprocessors to deal with system evolution in space in version control systems, they are limited to text artifact. They are error-prone, decrease maintainability and ability to evolve system, mainly when multiple features are tangled and intermingled over many files and many variation points. Thus, our goal is to have an extractive and directive software product line engineering approach for creating and updating the software product line, supported by a unified mechanism to deal with system evolution in space and time, combining the advantages of the software product line with the version control systems. And we believe that the first step to go in this direction is to provide a feature revision location technique. Thus, in this work, we show our automated feature revision location technique. This is a process that consists of input variants and gives to us output traces. A feature exists in multiple revisions where a feature and a revision are arbitrary and unique identifiers. A variant is a pair of feature revisions and a set of implementation artifacts. A trace is a mapping of a set of artifacts to a presence condition. Thus, the input needs the implementation of every variant, the set of features of every variant, and the revision of every feature of the variant. The output results are presence conditions, mapping every artifact to feature revisions in the form of a disjunctive normal form. The feature revision location process is an incremental process of creating or updating presence conditions, mapping artifacts to feature revisions. We use the artifact clusters to group clusters of artifacts that always appear together in the same variants. And we use the artifact sequence alignment by adopting a longest common subsequence algorithm to compare more than two variants when, for example, the methods are the same and whose statements must be aligned. We also use the artifact adapters to keep our technique independent of artifacts type, and we use the element counters to introduce feature revisions in presence conditions. Thus, our incremental process of locating feature revisions for every new input variant, we just increment the counters. And thus, we are able to trim feature revisions in presence conditions or remove the feature revisions when they do not hold anymore. Here we have an example of two variants. The yellow and green objects are variants, and they have in common the feature revision A1. They also have in common the artifacts A1, A2. Thus, we count for every feature revision in how many variants it appeared, and for every cluster of artifacts in how many variants it appeared, and for a pair of feature revision and a cluster of artifacts in how many variants both appeared together. Our evaluation was guided by two research questions. In the research question 1, we want to see if our proposed technique can locate feature revisions from a set of existing variants. And in the research question 2, if we are able to compose new variants by the set of feature revisions located by our feature revision location technique. Our evaluation followed 5 steps. In the first step, we mine ground truth variants from highly configurable software systems in version control systems to be able to have ground truth variants containing feature revisions. The ground truth variants, thus, we use it as input variants for our incremental process of locating feature revisions. At the end of the process, we have all the output traces, which we use to compose variants by joining the artifacts of the set of feature revisions. Then, the composed variants we compare with the corresponding ground truth variants. And finally, we compute metrics to quantify the relevant information missed and retrieved. The dataset used was from 3 highly configurable software systems. They have different domains, different sizes, and a considerable history of development. They have also been used in previous work. We use the dataset to mine ground truth variants, which is a process that consists of 5 steps, and you can see more detail in our paper. We also use the common metrics used to evaluate feature location techniques. The precision as percentage of the relevant information retrieved in relation to the total information retrieved. And also recall the percentage of the total relevant information retrieved in relation to the total information of the ground truth. And F1 score is the harmonic mean between precision and recall. We used 2 levels of granularity for comparison of artifacts of our composed variant and the variant of the ground truth. The file level, as we had different kind of files as C, C++, binary, and text files, by comparing the entire content, and also the line level, by comparing the lines of 2 code files, as the version control systems can only keep track of changes at the line level. As results, by mining ground truth variants, we could see that in the first 50 Git commits of Marlin, many features have been evolved over time. As example, in the second commit of Marlin, we could see 18 new features introduced and a new revision of the feature base. And the feature term starbed, for example, has 5 new revisions after being introduced, which characterizes the system evolution in space and time. Regarding the results of our research question 1, if we can locate revisions from set of existing variants, in the table we can see where 1 is the optimal value, that we achieved 100% of precision at the file and line level, and at least 95% of recall at the file level and 99% at the line level. We have few false negatives. In relation to the performance of our feature revision location technique for locating feature revisions, it took around, on average, 50 seconds per variant and no longer than 200 seconds. The outliers are in the systems with higher number of feature revisions. As we have more feature revisions and more artifacts to refine traces, more time we need to locate feature revisions. Regarding the results from our research question 2, if we can compose new variants from a set of existing feature revisions located by our technique, we achieved 100% of precision at the file level and 93% of recall. At the line level, we achieved at least 95% of precision and 99% of recall. Here we can see some false positives beside the false negatives. The false negatives are due to incorrect alignments performed by the longest common subsequence algorithm. And the false positives are due to invalid configurations that we used to compose new variants. Thus, we have feature revisions mapped to blocks of code of if and else, and our composite variant, of course, has both blocks of code. However, if we pre-process the configuration of these feature revisions mapped to this both blocks of code, we cannot have the ground truth variant with the both blocks of code, as the preprocessor will only be satisfied in the first condition. When answering the research questions, our technique proved to be effective for locating feature revisions in the dataset used. And our technique for locating feature revisions allows to compose variants with different configurations containing a set of feature revisions. As summary, we presented an automated feature revision location technique that located feature revisions artifacts with 100% of precision at the file level and line level of granularity, and at least 95% of recall at the file level and 99% at the line level of granularity. The runtime took around, on average, 50 seconds to trace artifacts to feature revisions for each input variant. In future work, we want to conduct experiments with industrial systems with different domains and improve the scalability for dealing with the growth of feature revisions. And finally, provide an independent and mature mechanism for enabling management of software product line at the level of feature revisions. Our data is available so you can access the artifacts of the paper and the repository of the tool for feature revision location technique and for MineGround 2 variants. Thank you for your attention.